Welcome back. Good news, bad news. Good news, maybe bad news. I don't know. It's my last lecture at Iowa. That's right. Hint, hint, YouTube. What's that? You get a picture. You can take all the pictures you want. Oh, there you go. That works. I'll do that. Yeah, afterwards. If people want to participate, no problem. Oh, yeah, that's cool. Oh, nice, nice. Very nice. Yeah, definitely. We could do that a little bit later. Yeah, look for the picture, YouTube. Look for the picture. So funny thing happened to me, as I'm leaving the university here. My Hawk ID password is now expired, and so I tried to change it. I did, and now I can't. I put a random set of digits in, and of course that was my problem. I was like, "Yeah, password generator," and somehow I didn't copy down the right password, and it's not in my generator. So I got to figure that out. Long story short, I can't get into Icon very easily, or on Eduroam, but that's okay. We'll persevere. One thing let's just talk. A couple announcements here that I'll try to post on Icon once I'm able to get access. Number one, the next week is presentations, right? So presentation, the final presentation is your last thing for the class. And literally, I'm hoping you take your homework and you make it into a 10-minute presentation. I put a rubric up as an assignment. I don't know if you saw that. I intend, basically, the gist is this. Every part of that homework, just spend a little bit on your slides. And then preferably when you start to show results. So basically, what is your data? Like, tell me the story of your data. What are you measuring? Then there was a question about correlation matrices. You can quickly summarize that. What's the average correlation? Something along those lines. It doesn't have to be the showing a table of numbers I'm trying to keep you from doing unless it's absolutely necessary. So you can move to that. Then you'll do with the model that you ran, right? And then what were the results? Basically, the model fit. Did you have to make modifications to your model, right? Finally, then what's the final model? What are the results made? The end. Nothing really fancy. Again, 10 minutes. The goal of the presentation is to basically show everybody else in the class your different measurement contexts, because when you get locked, the rationale for me is when you get locked into measuring the same thing over and over again, you sort of lose sight of what the whole bigger picture is, and seeing other people doing the same method used in different contexts helps expand that. I say that from personal experience, also from industry experience. We have a whole testing industry that's locked into measuring one-dimensional things, and the inertia there to tell people how to not do that is really difficult to get over. And I think a lot of exposure to same methods, different contexts would be useful. So that's my goal for this. Questions on presentation? You should all have your graded homeworks. Almost everybody was great. They did a great job. Those of you who may have had a couple comments to address, you're welcome to contact me for help or the teaching assistants. But basically, the way that the score, if you want to talk about points, grades, I don't like to talk about that, but we all need to. Your lowest homework grade is dropped, right? And you already have your midterm grade. I haven't made the final grade calculation for the lowest homework grade, but you can do that yourself. And so this is the last remaining bit of the grade, which is the presentation is about the same weight as the midterm. Okay, so that's the intent. Sound good? Finally, a couple of the notes on that. I really wish I would have been able to post it ahead of time, but I'll tell you this and I'll post it when I get in. No, we're not going to be in person for this. It'll be on Zoom. I will be at the Cedar Rapids Airport, unless you'd like. If you have a flight, you're welcome to come visit. No, I have a business meeting I have to go to. It starts Thursday, Friday, so I have to fly out anyways. Unfortunately, the flight schedules have changed, and so my flight's at like 4:20 p.m. So I'm going to get there very early. We'll all be on Zoom. Zoom. Nothing will be recorded. None of this will go to YouTube. None of this will go to the internet. It'll all just be between us. So you can be candid, frank, honest, not have to feel like you're auditioning for a role on some weird soap opera that no one wants to be part of. Sorry, YouTube. But then what I will do also in this announcement link is I'll send a link for the order of the presentations. So it's like a sign up time. And what we'll just do is just put your name down. If you don't care, you can just wait till the day it is and we'll just put you in on that day. But basically, we have 9 students, so there's 9 presentations. We've got, 180 minutes of class total, but that's 90 minutes of presentation time plus break and whatever else. So we'll be plenty of time, should be plenty of time to do everything well. Questions? Yes. Oh, yes, absolutely. Yeah, I was planning on doing the 10-minute for presentation and then like a 5-minute gap between when one went in and one would start. You can use some of that time for questions. Absolutely. And actually, since we'll be on Zoom, it minimizes the time it takes for someone to move and be ready. So yes, question. I wish I could. The what? Say the question again. I'm sorry. I wish I could get in, but I can't get onto Icon right now. Oh, sorry. I was trying to challenge you to have no tables of results. I should have said that more. I was hoping to, I wish I would have. That was a thought I had, and I wrote that, and then all of a sudden I'm like, oh, wait, I didn't come back to that. Sorry about that. So, when you present results, it would be great if you did so without tables, because tables are the death of every presentation. So, it's a challenge. You don't have to. You have the points associated with your. So, think of it this way. If you're looking at correlations, how would you express correlation without a table of correlations? Think of it, grab all those correlations, put them in a histogram or a box and whisker plot, right? Take a, what I'm trying to look for is like all that numbers, all the numbers that you try to parse. We all do this all the time. So I'm not here to throw any shade at anybody, but I'm just trying to get into good presentation practice. Whenever there's a table in your presentation, that's audience killer, right? That's attention killer. That's whatever. So how do you overcome that? Well, sometimes you have to do tables. Let's just be that honest, right? And in that case, highlighting numbers that stand out, like visually, something to offset them to guide the focus is good. Similarly, when it comes to other versions of results that you normally see in a table and a paper, trying to make them into a summary that's quick, relevant, something along that. So correlation can look like that. You could think about, like, I don't necessarily need to see the A and B parameters for each of the item response theory models if I see the item characteristic curve, because that's information embedded in that curve as well too, right? So that's another way to describe what you're doing. I think the hardest part would be model fit statistics. I don't know how to visually display them because each number is relevant only in its own context. So you can't compare them. You can't go and say, oh, look, the RMSE for this one is, RMSEA is 0.06, but the CFI is 0.99. That doesn't, putting those in the same table probably won't work. So that's where I would say,
That's the challenge.
right, yeah. So my challenge to you is to try to think about building the presentation where you don't just have a table of numbers, you have some type of quick display that gives you the same information. Does that help answer it? Yeah. Again, it's a challenge. I don't want you to spend forever on it, but you had to make a graph in the homework, and that wasn't accidental, right? So, okay, other questions on this? No. All right, I'm excited to see your presentations. I really enjoyed seeing your data analyses and looking forward to the end of it. So with no questions on that, then we can get to the lecture. I have a lecture and I have an R set of syntax, and we may be doing some things impromptu, we may not. It's funny because the way I've structured this class where I put path analysis first and I kept hinting back to it with that beginning example, I feel like we already have gotten to this part. So what this lecture represents is the practical aspects of doing structural equation modeling, and then trying to at least get to that. I can't guarantee it's going to succeed. But then after that, one of the considerations of what I had posted, that first path diagram at the beginning of class. Now, I'm not going back to that example. I thought about doing that, but I thought, nah, let me go with another example with real data, because the fake data always seem to work really well, and the real data, you never know what you're going to get. That was also the reason why I am, yesterday there was a lot of shouting in my room, in my office. I'm just kidding. Real data is,
Frustrating.
can be frustrating. Okay, so let me dive into the lecture first. So structural equation models, if you leave this class and someone says, what's a structural equation model? You can say it's a path diagram, path analysis with latent variables. How's that sound? That's I like that word. That's Rod. I learned that from Rod McDonald's definition. I like that definition. There are people who say structural equation modeling is everything, like it incorporates a multi-level model as a structural equation model, or a mixture model as a structural equation model. And I think that represents people who have done other things, but have been started their training in structural equation modeling. But to me, this is what this is. So that is path analysis and then measurement models with latent variables. So I'm going to refresh some of those memories and doing this, and in doing so, talk about some of the concerns in building structural equation models, right? Because it's like we had this path analysis stuff going on, and then we took a break from it, and we did measurement models, and we sort of hinted at putting them back together. But what do you do first? You stick them all together first? Do you put them in one big model first? How do you build a model together when you have parts of it that are measurement and parts of it that are not, with a goal towards having model fit, first of all, and then making interpretable results, right? And then we got some examples as well. Stop me if you have questions. All right, the underlying theory. I just mentioned this. It's like I made these slides. The structural equation model consists of two parts, right? Measurement models, if they exist, for each latent variable, and then path analysis, or a series of simultaneous regressions between latent and observed variables. Right? Those are the two parts. Some structural equation models may not have one of those parts, right? So every measurement model technically is a structural equation model, even if it's just a measurement model and there's nothing else being predicted in it, right? Every path analysis is also a structural equation model, even if you don't have measurement models involved, like we saw in the path analysis lecture, right? And so you get this is the interesting pedagogical twist of how we teach SEM, is that we talk about both of these in isolation. We say, oh, path analysis, we're going to put some of that in your generalized class. I think that's where many of you saw it first from Lisa. And we'll put, measurement models in classes where sometimes they're called that, like here in this class, and sometimes they're not even referred to that, like in item response, a lot of item response theory classes, not all of them, right? And so, putting them together sounds like, oh, that sounds easy. They're all part of the same thing. It is pretty straightforward. It is one extra step sort of to combine them both. But the problem with that is model fit, particularly with the measurement, when you take a measurement model and you stick it into a structural equation model, right? Because the measurement model, if you remember degrees of freedom, are degrees of freedom that come out of the model fit. Remember what that represents? The difference between the number of parameters in a saturated model and estimated in your model, right? Okay, so in a measurement model, if you have more than just a handful of observed variables, the degrees of freedom gets very large because the saturated model is accounting for all the covariances between each of those observed variables. But your measurement model, for every variable you add, let's say it's a structural CFA model, you're only adding one loading potentially, right? And maybe one unique variance that counts against it. So for every time you add one new observed variable in the CFA approach, the number of parameters go up by 2, maybe 3 if you count the intercept. But every time you add a variable, when it comes to the saturated model, the number of parameters go up by the number of variables that are already in the model, right? Plus 1. Because if you think about it, you're adding a whole row of covariances to that covariance matrix. So what you end up seeing in the structural model, in the degrees of freedom, as if you have a unidimensional measurement model, right? As the number of items goes up, the number of parameters in the saturated model goes up almost exponentially, not quite, but it does grow in there is an exponent to it, yes. Whereas the number of parameters in your measurement model go up linearly. So what that means in terms of degrees of freedom is there's a lot more degrees of freedom often in measurement models, right? So let's talk about why degrees of freedom are important. The secret to model fit is, let me back up. The number of degrees of freedom you have indicate how far or how much your parameters have to get stretched to cover every one of those unique covariances in that covariance matrix, right? If If you have 0 degrees of freedom, you're just identified. That means your model perfectly recovers the covariance matrix. If you have a degree, 1 degree of freedom, right? That just means that there's 1 extra covariance somehow that the parameters have to accommodate, right? But when you're talking about 100 degrees of freedom, it's a lot harder job to do. It's a lot harder job. So the argument I'm laying out for you is, you have to have a lot more strong and verifiable theory to have a good model fit when your degrees of freedom are large. Does that seem controversial? I don't think so. Right? It's just it's an accounting game, right? Some minor deviation from what it should be, just by chance or by sampling fluctuation, could cause you to have poor model fit in your model. So guess what happens? So that's measurement model, right? So now let's imagine we're going to bring a measurement model in, just like we did that first class, where we've got 1 latent variable we called happiness, 5 indicators of it, right? And now we add the prediction variable to it. What are the degrees of freedom there, right? So before, if you had just added up a sum score and made a regression out of it, you'd have 0 degrees of freedom, because all univariate linear regressions have 0 degrees of freedom. They're just identified. But when you go and add that extra variable as a measurement model, now that variable's covariances with all the observed variables in the measurement model has to be spot on as well too. And therein causes huge problems. So that's the problem with model fit. Sound good? I'll show this to you as we go forward. Questions on any of that? Okay. Remember endogenous and exogenous variables? We can go through this quickly. Endogenous is something being predicted, anything with an arrow terminating at it. Exogenous varies but not predicted. This is what we showed before. If you want matrices, I can show you matrices. I didn't put those in before, but that's the Kaplan book. Okay, enough with that. There we go. I just thought I'd throw it in there. If anybody wants to map what Kaplan does with the matrices, you can go and take this. Remember that Kaplan book? I should have probably put this slide way back in the day. But I deleted it back then, but now I'm like, I should probably bring it back. Okay, so as much as I told you that tables are audience killers, so are equations. And I just killed you. So I get it. Now, that depends on where, actually I should stop with that. If here in maybe Schaefer Hall, where the statistics department is housed, those equations are the story, okay? But for us and for most audiences that I speak to, you put that up on the screen and it's just like putting in, yeah, exactly. You remember the old phone books? I don't know if you remember those. If you just took a page out of that and stuck it up here. I'm talking about number complication. I don't know. You don't have to remember the old phone books. I barely do, but yeah. Okay. Anyway, that is just for you. We can do factor analysis, right? We've got 5 observed variables. Got our measurement model. Go. And of course, you can do matrices with it too. There's that famous equation right there. But we put it together and we get something like this. So the example I'm going to give you today is an actual data example that I had a hand in collecting many, many years ago. And I'm going to tell that story real quick. I, as a grad student, worked in a lab at the University of Illinois that was concerned with problem gambling. This was at a time before gambling was widely legal. Now, literally, you can't walk out of this building without having an ad for gambling somewhere, right? But at the time, it was pretty. We could see this trend coming, and the lab, and the professor had gotten a grant. I'll call it a grant. It was from a set of industry casino operators that were trying to show that casinos were concerned about people spending too much money gambling, which I think to some extent they may be. They want the people to spend money responsibly because that way they can keep coming back and spending money. But, maybe not. You can look at it cynically, but, they gave us an opportunity. So we actually went to a casino boat in Illinois and collected data from 144 people. I kid you not, right? And as part of that protocol, the casino worked with us. We actually had some of their security tapes about how people were gambling. So we basically had to recruit people from a roulette table, roulette with the spinning wheel. Yep. And one of us had to sit there and sort of monitor who was playing because we wanted to get 45 minutes of video of them playing roulette, sort of look at their betting patterns, although we never did. And then we were going to, as soon as they left the table, we're going to interrupt their gambling because that would be against the rules. As soon as they left the table, we'd come up to them. The person sitting at the table would signal to someone standing behind, hey, "Go get that person." We go over to them and say, "Excuse me, would you like the chance to win $200 or whatever it was? Just come with us." And so we would take exactly the casino let us take them off the casino boat to a back room. By the way, it's called a boat because of the laws in Illinois. You can't have a casino at the time. You couldn't have a casino on actual land, but the river was okay. Never mind the fact that the boat actually never traveled. It just was sort of docked and it may have, yeah. So that, anyway, talk about the weirdness of all this. Take them off the boat into the casino's back offices, right? I'm thinking like, I don't know if you've ever watched mafia movies with gambling. It feels like that a little bit. Actually, it was pretty clean and comfortable. They took a survey. They had this survey about items that asked them how much they gambled. And then they went on their way. But here's the catch for us to be here's the point of the story. For us to actually be able to track who was playing roulette, we couldn't just sit there and watch the roulette table because we're sitting literally taking up a spot someone could be betting. So we actually had to gamble. And each of us had a turn at least to sit. No, I did not. But the money we gambled with was the grant money. So that was the point of this story, which is whenever you see gambling and you see me doing this, it's because we gambled with grant money. Yes. And the PI at the time, who will remain nameless, although those who were involved certainly know his name well, I believe he turned to us and said, "Well, you're gonna be there a while, so it's not likely you're gonna win, but don't run out of the money. And if you did happen to win, I'm not gonna know about it." All right. So how about that? Your RA ship. Can you imagine that if your professor and your RA is like, "Hey, we got to go collect data. It's going to involve you gambling." All right. Ironically, that was the first time I'd really gambled a whole lot, and it's sort of like, "Oh, this is kind of fun." And then I used my own money. I'm like, "Oh, this is really not." So it's addictive. Anyway, here's what we want to do. It's very similar to where we started the class this year. We have 3 Likert type items. These were all 6-point Likert items. The numbers just indicate the number on the scale. From my knowledge, basically they're asking about gambling tendencies. Let's imagine that's a latent variable called gambling. And then turned out we wrote a paper about this. This is the first paper I published. It was in Psych Methods, but it wasn't it wasn't about the grant. The grant was also an interesting experience academically, but I wrote a paper about this talking about how we could use a classification method to look at these data. And to get that paper published, they didn't want us to have 144 people from the casino. They wanted a much larger sample size. And they said, just collect data from students on your campus. So we did. I was at the University of Kansas. I went through IRB. I gave students the same survey that I did here. I got my sample size up, and I got the paper published. Yeah. I had to make this work. The reviewers needed this. And I was like, and I need this paper. So I did. I agree. But we're going to use that today, yes. That was the thing. We couldn't. And there's like what we could ask them, we could ask them to self-report. Have you gambled? Do you gamble regularly? And most of them said, absolutely not. Turns out actually most of the normal population at that time also didn't gamble as well too. I think it's probably a little bit lower now, but yeah. Yeah, right. Oh, I completely agree. And actually, we tried to make that distinction too. We did say at the time, because lotteries were available, had been available widely since the 80s, I guess. And so we did make that. But even then, when we asked what type of gambling they did, it was hardly anything. So, yeah, most of the student sample claimed to have never gambled or not gambled. Mm-hmm. So the paper was more of a proof of concept for method. But yeah, no, so what we're going to do today, we're going to try that. Right? What we're going to say is this. I have the variable whether the person was a student or not, a 0, 1 variable, coded as a 1 for a student, I believe. I don't know. I have to look in the data again. Anyway, and what this would tell us is what? It would say, are students different on their average gambling, right? Is there an impact? Is there a group difference between students and non-students on their average level of, I guess this is a tendency to like to gamble scale, right? Does that make sense? But after that, I don't know. I don't know. Yeah, that's just the absurdity of the whole review process as well. Oh, sure, you want us to gather students, and then it's okay. Got it. All right, so the measurement model, as you know, is this section here with the circle, and then the structural model is the other right-hand side of the section with the circle, right? Okay. And I just realized this slide has a typo too, of course. But we're assuming this assumes the gambling construct is the same for both students and non-students. So that's one thing. Last week was Thanksgiving. The week before that, we talked about measurement invariance. Remember that? And we had to go through the process of establishing whether a measurement model was measuring the same thing between two groups, and if so, how do we quantify it? But this right here ignores that. So did my example in the beginning. So what do you think? Can I just run this and call it good? The answer is going to be no, right? So this does assume this is the same, but we need to verify that. That's a huge assumption, particularly when you look at these two groups. Students at the time, circa 2006, who really didn't gamble, and people from a casino boat late at night actually spending their real money. Yes. Mhm. Yeah. Oh, you can get much bigger than that, but this is trying to distill what we're talking about to the core, as the didactic example, right? So if you want to go see examples that are much bigger and better, Lisa has some from her previous version of it. I will tell you, not bigger and better, but I'm saying like more complicated, yes. But the concepts I'm trying to instill in you here come from this exactly. And this is sort of the smallest unit of those concepts. I think I can do that in a way that at least is understandable in class. Does that make sense? Thank you. But yeah, I mean, I'm happy to share more. Actually, true story. You know, I've got Lisa's like, you can use my materials. This is actually my slides, as you can tell, because there's typos and stuff. But I looked at her slides, and she had this really complicated path model in, and I was like, I'm just not going to do that because I feel like I don't know that I can get through everything I want to say with it for it. But yes, other questions? So yeah. Mm-hmm. The structural point is looking at differences based on. That's it. Yeah. Okay. Yeah. Exactly. But again, when you see this right here, it looks pretty like, oh yeah, that's the straightforward extension between path analysis, this part, and measurement models, right? That's pretty straightforward, but it's not that straightforward because this now makes the assumption that there's no direct effect of student on each of these variables. And there's no interaction of student and gambling on these variables. How's that sound? You don't think about it that way, right? But now that's a part that we have to go evaluate first to really do this well too. I see the frowns. You see what I'm saying? Right? You don't see that when you look at it. And we've been talking about this all year, and I'm like, oh, I got to leave it this way. But here. So let's go over, actually, this is the slides where I go through my slide. I'm going to go into the syntax real quick. Is that all right? Let's see. How's the size of the font? Everybody okay? Excellent. That is a redundant question for YouTube. Sorry, YouTube, you don't get a say on this one. Okay, so the very first way we first thing we got to do is we got to go to the measurement model. So when you look at this model here, the key in building a structural equation model where you have measurement models is to go to your measurement models first, build those so that they fit, right? Why? Well, the measurement model is the source, the biggest amount of degrees of freedom, most likely, in your structural or your path model. So you start there and you get good fit to that small segment of the bigger model. right? Now, with 3 items, tell me, what do you expect fit to be for this measurement model? Perfect. Yeah. This isn't going to, this little example here won't give us fit. But ideally, what we would do with the measurement model is we go see if my measurement model fit. We have to maybe perhaps refine the measurement model to make it fit, right? So when I do this, I end up with these estimates right here. There we go. Perfect model fit. 0 degrees of freedom. This, remember, this model test baseline model is the test between the independence model and the saturated model. So the 3 correlations, at least one of those is non-zero. That's what's that telling us right there. And you get our point estimates right here, plus our R squared. Okay, there's our measurement model. Ta-da. All right. Now, we could dive in and add the structural equation model just to see what works. Now, we know this is tenuous. Why do I say it's tenuous? Because we didn't establish that the model, the measurement model, is non-invariant or is invariant across levels of student. So this is the naive way of doing SEM. Let's just throw student in the model and see what works out, right? Right. So you see what I'm doing here. We've got our measurement model. That's the same. Then once we've defined gambling as a latent variable, we can use it and we can say, oh, let's predict it with student. Oh, let's not do that. Right here on this line, right here. Right? That makes sense? Now you've seen that code for quite some time. We do that. Then we get this for model fit. Let's take a look. Now all of a sudden, we have 2 degrees of freedom. Right? That went up because now in our model, let's do some math. How many, this model right here, is this picture. This is what we just estimated. So how many endogenous variables are there in this model? 4 if you count gambling. How many endogenous observed variables do we have? 3, right? Even though it's being predicted by something that's not an observed variable, that's weird, but yes, it happens. How many exogenous variables? Just 1, right? So for observed variables, we have 4 total observed variables, right? So our covariance matrix for that will have 4 unique variances and 6 covariances, right? So when you get to this model, the 2 degrees of freedom are added because when we went from the 3 variables with a 0 and we added that 4th one in, now we need to worry about those 3 unique covariances between student and all of the observed variables, and then the variance of it as well too, of student. Right? So that's where that comes from. We only get 2 parameters, a variance and a slope for it. You can see the model fit is not great, but we can take a look at results. What does this indicate to us here? Here, this slope is what we're talking about, right? So student, the variable is a 1 if the person is a student. I can tell you that right here. So what does this regression slope represent? That's a question that's not an SEM question.
How much difference between the groups?
That's it, because student's a group variable. People in the student group are negative 1.162 lower in the mean of gambling. Now, what is the scale of gambling? Well, the gambling has a variance of 0.313. Right? So 0.313, or if you want to talk about it from a standardized point of view, that std.all variable right here, that thing tells us about a little over one, a little under, it's about a half a standard deviation lower on average for students. Does that make sense? Okay, now, a couple of notes on that. Number 1, here, we can see before the variance of gambling was 0.407. Sorry, you can't see that. You see this, 0.407. Right here. And now, in our new model, it is now 0.313. So what you can talk about is sort of the reduction or the R squared for gambling. The nice thing is we get that out right here. Right? There's our R squared for it. So 0.293. So how are we doing? Questions on any of that? That's what we have thought about. Yeah. The R squared that we see here is 0.293. So we are explaining about 30% of the variance of the gambling factors, the student variable. And usually, knowing the way that the students work, so interesting story about this scale. We had been using a similar scale that were binary items, say yes, no, right? And a lot of these items were like, I have stolen money to pay for gambling before, right? Something that would take a lot for someone to say yes to. And we thought, it's all the yes, no part of the items that are causing this sort of everybody picking no. We thought that was one of the thoughts. So they built a bunch of I wasn't part of the lab at the point. They built these Likert items thinking, there's more response categories. People will still, will spread out a little bit more. Turned out, no. When people don't gamble, they really don't gamble, and they strongly disagree with anything that suggests that they would want to gamble either, right? So it was a case, this data is a case in like all sorts of how a rare event data and models work together. Anyway, getting off track with this. Let's now detour for a second and think about not doing the structural equation model. Let's think about doing an invariance analysis on the measurement model. Because the invariance analysis on the measurement model will tell us whether or not the construct is measured the same by the two groups. Does that make sense? So I'm going to not take the student variable and put it in the analysis. I'm going to just do my invariance analysis. And I'm going to start with the configural, and student will be my grouping variable, right here. So first is the configural model. Do you remember what the configural model does? Anybody want to put that into a quick definition? Separate parameters for both groups, right? That's right. You want to make sure that the structure itself is the same with 3 items. It's going to fit in each group, so not really worried about that, but it's our baseline model as well. And you'll note perfect model fit, right? Because we have 2 of the same model in each group. Now if you look at if you eyeball some of the estimates, you'll see, those estimates are somewhat different perhaps. So that's what we have to go and figure out with this approach. Okay. So the next model that we estimate is the metric model. The metric model takes the loading variables and sets those equal. I should have noted the configural model, all the factor loadings are unequal, all the item intercepts are unequal, all the residual variances are not unequal. But then to identify the model, because we're estimating every factor loading in each group, we have to use a standardized factor to do that, which means the variance of gambling for each group is set to 1, and the mean for gambling for each group is set to 0. Right? So it's almost as if we did a standardized factor 2-group analysis and just put the results on top of each other. Okay? And actually, I believe, don't see it. It used to be the case, I can't remember which software it was, where they would actually give you the log likelihoods by group, and you'd see that they just summed the total. It's effectively like we ran 2 separate analyses is what this is. Okay. So now we get to the metric model syntax. Here, 2 changes. Number 1, the factor loadings, we've added constraints to. So L1 and L1 means estimate the same loading for item 1, etc. Number 2, we had to free the variance for one group of the gambling factor. Because once we make this constraint on the factor loadings, we're able to estimate the variance in the second group. And because the variance and the loadings are highly related, we do not need to make the constraint of 1 here. Otherwise, we're artificially imposing a very strong assumption onto our data. Okay? So, what do you think? Do you think students and grown gambling crazy adults have the same structure with loadings? Let's find out. Okay, so we're going to do a ANOVA test. And there we have it. Yes. Now I'm looking at something and yes. So we have 2 degrees of freedom here, even though we just put constraints on 3 loadings. And the reason we have 2 degrees of freedom is because we had to free that factor variance, right? So it's not 3 loadings that we're testing here. But yeah, I am going to say that's pretty close, right? And why I'm saying that, so normally you'd say, oh, what level of alpha do you want to worry about? So remember in the invariance analysis, we start doing p-value, we start looking at hypothesis tests fast. We look at a lot of them. So I think a lot of times when you'd say, oh, I want a 0.05, alpha level, the number of a test that you do, the likelihood of having one not be significant by chance is so high. A lot of times people make this much lower. So I'd say 0.05 is fine. Just leave it. So let's leave it. Loadings are the same. That's great. That means gambling largely is the same construct. But the propensity, like the average, may be different in groups. And that's what the next step will do to tell us. Sound good so far? Okay, so let's do a scalar. So in the scalar model, remember we start with the loadings being equal. Had we have needed to make one or more of these not equal, we would then omit what we're doing in this part. But the scalar model talks about making all the item intercepts equal. So the 3 item intercepts now are estimated to be equal across groups, but similar, now we need to free the mean, the factor mean for gambling. And by the way, if you're like me and you're putting this together the day before you're teaching this, just to make sure we have a point, you'll forget this part and then have to redo all of your analyses. Don't forget. Right. You have to free this to make it a better fit. Otherwise, you're assuming the means are equal, which we assume they're not going to be the factor means. So we estimate this model. What do you think? Do we have... Oh, no. Hang on, let me think where you can see that. Actually, let's do this. There we go. There we go. Yeah, much easier to see up here. Okay. So I can, for the sake of class, be like, yeah, that p-value of the metric model, that was 0.056. We're ignoring that. I don't know, can we ignore this p-value? Like even R is yelling at us with these asterisks. Hey, this is different. Yes. Angry R voice. So let's investigate, shall we? Now, I did clean up the code from the investigation of the modification indices before. With the way that Levon is doing that, I get this warning message every time I do it, but that still seems to work. And so here, this tells us in order, the x2 column is the chi-square. The parameter I glued in there at the bottom, right? Which one to look at, 1, 3, or 5. So that this is what, if you can look at it, I order them by decreasing levels of chi-square. The bigger the chi-square, the more like power that test has to detect the group difference. So each one of these chi-squares has a very small p-value, but remember, these are like saying, what would happen if I added one of these parameters to the model and re-estimated it? So you might be thinking, oh, I don't have anything the same here, but remember, this is incremental. These are one-at-a-time tests, right? So what I would do is take the one with the highest chi-square, free that parameter, rerun the model, and see if we need to add another. How's that sound? Does that make sense? All right? What do you think? Have a look to you. That looks... Okay. Just wondering if that was skepticism. I'm okay with I'm a skeptic myself, so I appreciate some skepticism. I wanted to work on accuracy if that were the case. All right, so this is the one where I take only item 3 is intercept and free it. And now take a look at our chi-square.
That's great.
No, the chi-square now says there's no difference between our model and the metric model, right? So what am I just do there, right? This is an indicator of why modification indices are 1 degree of freedom, 1 parameter tests, at least in the way I've output them. There are multi-parameter modification indices. You probably have a use for them in some cases. I don't tend to use them very much or see people using them much. But this is telling us now if we just took item 3's intercept and allowed that to be different by group, we basically have the same model fit we had in this measurement, in the metric model. Pretty cool, right? So here, if I go back and just see what that different by group is, in the non-student group, the intercept wanted to be 0 or 0.87. And in the student group, it wanted to be 1.526. That's quite a big difference. Interestingly, an intercept of 0, or close to 0, means the expected score for someone in the not student group when they are at their average, actually no, when the latent variable is equal to 0 for this group, should be close to 0. Right? So I was about to say, oh, but remember, here what it tells us is the gambling group mean right now is 2.971 units high, or whatever those units happen to be. So anyway, intercept you would normally interpret as the expected value of the response when the latent variable is 0. It still is, but the question is, what does it mean for a latent variable to be 0? That would be a person far below the average gambler on the latent variable scale in this case, right? In a standardized factor, the latent variable mean is 0. This is someone far below the average non-student. Now, the interesting thing about this number is we have Likert data, and our lowest number in our data is a value of 1. Got 50 seconds before break. So that's an out of bounds type of estimate, potentially. I probably should be running IRT with this. So why didn't I do that? I couldn't get the model to converge. Model convergence blew me up on that yesterday, so I just decided to punt on that. But part of the reason is these data are so skewed, it's really hard to figure out some of the higher category boundaries. And those, like the category submodel intercepts are difficult. Yes?
So, I was working, I was working on my exam,
Mhm.
and that the convergence not achieved is something like I got a lot. So in that case, do we have to rethink the whole model?
No, it's troubleshooting a convergence issue is sort of a bit of an art. And there's, quite frankly, 50 different ways why it may not converge. One of the easiest ways to try to ensure convergence is to, if the convergence error was it terminated because it ran out of the maximum number of iterations, to exceed that. My error wasn't that. I had an matrix inversion problem that I couldn't necessarily solve. I probably could. Levon has some other ways I haven't investigated yet to try to fix that. But if you have a number of iterations reach the maximum, just figure out where the option for the number of iterations is and add that.
Yeah, so
To
I
it.
was using Stata for that.
Mhm.
I tried iteration 50 and after go, but later I realized my model is too complicated.
Yeah, it may take. Yeah.
Do the whole convergence thing and
So this gets into a really technical topic quick, but I'll give you the short of it. If you're using IRT, the likelihood, the method it estimates, depending, I don't know what Stata's method is. Levon uses something called a limited information. Stata may use maximum likelihood, which is marginalized, so it has this numeric integration. But either way, it can be really slow to converge in binary data because binary data likelihoods for that are much less well behaved than our continuous, like the normal distribution would be. But that doesn't mean. But if you have binary data, you got to use it. Yeah. Yes. Yes. Then the next step would be to see if you have a dependency in your data. If sometimes in Lavon it will return if it reaches the maximum number of iterations, it will return the parameter values at the last iteration. If you look at those and any of them seem abnormal, I mean, like if we're looking at loadings and we see these numbers around zero 0.5 and you see one that's 30, that's probably abnormal. Those types of are indicators of which items may be causing the problem, and it may be the case that removing an item that has weird parameters may do that. But I'm happy if you have a specific problem, I can help you troubleshoot. Yeah, I know we're on break. Let's take a break. I can answer more questions when we get back. How about 1:33? We come back, or 1:33 p.m. Central Time. Okay, start again. Back from break. Any other questions on where we left off here? This being the 1 degree of freedom parameter change for the metric model, scalar model, excuse me. But it looks like it fits though, right? Should we continue? Okay. Next model from here, I don't need a debug point, but let's go to the residual model. So now in the residual model, you'll note I just freed all 3 residual variances. A lot of times you might leave the residual variance for one of the items. Like if we saw item 3 was non-invariant for the intercept, you might just leave that as non-invariant for the variance too, but that's not, 6, 7. There, I said it. No, I shouldn't have, right? 6 of one, half dozen of another. That's the old man version of it. All right. And what do you think? How many of you think residual fits equally well? Let's find out. Oh no, the scaling factor is negative. This could happen sometimes. Well, I wanted to show this to you. This is the fun thing with real data. What does that mean? Scaling factor is negative. Well, what it means is this scaling factor right up here, the scaling correction factor is what takes our likelihood ratio test and adjusts it for non-normal data, right? And so this thing being negative can't happen if you want to do a likelihood ratio test. So for some reason, it turned negative. Well, it turns out I'm not going to do a likelihood ratio test. I'm going to take that to mean there's something wrong with our model. Okay? So I'm just going to look at modification indices. And here we have them, right? I don't have the overall chi-square, but I do have the relative change in chi-square if I free one of these parameters. And you'll see this first value has a chi-square value of 283. That's huge. That's a big number, right? Well, think of it this way. This thing should be distributed as a chi-square with 1 degree of freedom. A chi-square with 1 degree of freedom, the 95th percent, basically your 0.05 cutoff critical value is 3.84. That's at the 95th quantile of the distribution, right? Now we're talking about how many, much further than that, right? This is massively big under that null distribution. So this would tell us we should free parameter R5. So let's do that. We did. And now, look, we can get the likelihood ratio test working. So back to when something breaks in these models, sometimes it's an indicator something is not working in the model itself. In this case, it's working better now because this parameter that really wanted to be separate is allowed to be separate, therefore allowing us to estimate more values elsewhere. This is different, though. It means at least one more of them may need to be different. So before I look at the parameters, let's just do that. Let's figure out which one. Sure enough, it's now the first one, first items. So it's interesting about this, why this is the case. Think about what this residual variance is representing for each of these items. It's what's left over after you predict it with your latent variable, right? Well, in one group, the student group, what's you're predicting tends to be very low responses, 1 or 2s, which means the variance is going to be very small, which means anything left over is also going to be very small. Whereas in the other group, now there's a lot of 1s and 2s, but there's also 4s, 5s, and 6s. That variance is likely to be bigger. So what I'm expecting to see, I haven't actually gone to the results yet, I was going to do that on the fly in class, is to see that the parameter will be bigger in the non-student group. But let's find out, right? So again, here I'm now freeing the first item, and now we're not there, but I'm going to ignore it. So the residual variances are on the cusp of not needing to really pay attention. Sometimes people debate the use of it. I think you still need to pay attention to it. But again, I'm concerned with all these hypothesis tests I'm doing. I might not want a 0.05 for this criteria. I might want 0.001 or something like that, right? To reach it. So let's take a look at this result. The estimate for the non-gambling group for these two variances is 1.454 and 2.106. And in the gambling group, they're much smaller, 0.6 and 0.4. And this is what I was talking about. If you look at the distribution of the responses for these items, it's here. Let me see if I can do it. What is the name? Data 01. There is one of those items. All right. Looks like a stair step. There's another. And there's the other. They all kind of look the same. A big pile of people who say they don't do or think about gambling a whole lot because they just don't gamble. That's what's happening. Cool. So now we've done it. This is it. We've established partial measurement and variance. Let's go and think about the next test that we need to do, which is really what the point of the structural equation model was in the first place, which was to determine whether there's group differences in gambling for students, average gambling tendency for students versus non-students. How we do that? Now, remember, the structural model is a little different. This structural model syntax represents us putting constraints on parameters now, because each group already has a different mean, a different parameter for the mean, and a different parameter for the variance. I have to go back and constrain those to be equal. That is what I did. And when I do that, I can tell you that there is now a 2 degree of freedom difference between it. I just let the variance and the mean be equal. That's the two parameters. And that p-value is quite large as well, too, saying, yeah, there is big difference between groups. So now let's evaluate that difference, shall we? So I'm going to grab the results from before. This is the model where in the student group, the mean of gambling was set to 0 and the variance was set to 1. So if you look at the non-student group, the mean is 3 points higher for gambling. Now, again, you have to say 3 points of what? Well, gambling's variance is 2.67. So that would represent a standardized effect of 1.898. So basically, non-students on average are 1.8 standard deviations higher than students in their gambling tendency. How's that sound? Not surprising. Now, let's go back, though, and compare that to what just came out of the structural equation model we tried before. Remember, the structural equation model just before all this, right here, treated the measurement model is being invariant across student, right? So if we look at its summary, we saw that the standardized effect was actually, now student's a 1, we coded it opposite before, but basically gamblers are half a standard deviation more than a student. So you see what ended up happening. The model constraints that we built in not only changed the mean, but also changed the variance of that parameter, and it grossly underestimated the difference between groups, right? Our difference was actually 1.898. The other one was not. So let me ask you a question. This is more of a modeling question, a more of a not necessarily structural equation modeling, but now we have two models to tell you the same thing, right? In one model, we say there's not only a group difference for the mean, there's likely a group difference for the variance. And in the other model, we say, oh, there's a group difference on the mean, but the variance is constant. Which model do you believe?
Which one has a better fit?
Oh, okay, so let's talk quantitatively. How would we evaluate that? This is me trying to put you in this situation. Ah, good. We don't know that these are nested models, so let's look at AIC and BIC. Okay, I think that's a great strategy. Let's do that. AIC and BIC would be, actually, let me see if I can actually do this, I'll be surprised, but. Yeah, I got a result. I don't really care about the chi-square difference. Ignore the chi-square right here because they're not nested models. But I have the AIC and BIC. So if we look on AIC and BIC, what we're looking for is the lowest value of both. And in both situations, we would pick our model. Now let's think logically though, right? What is the difference between this model right here and our final residual invariance model that fit the best that we did before? What's the difference? Let me get the results. The difference is this, all right? We still have the gambling by student effect. That's the mean difference. But difference number one is there's only one variance left over. So what this model assumes about our values is that the variance is homoscedastic, right? That gambling, there's only one variance to it, and both groups share it. We just established in our model that's not the case. I didn't do the formal test, but that we could have broken up the structural part into one for the variance, one for the mean. But we can look at the numbers; they're very different, right? So number one, what we know is that there's heterogeneous variance in each group for gambling tendency. That's one parameter difference. But the other parameter differences are on the measurement model, the things that we had to allow to be free to estimate the measurement model. And the way you can tell that is anywhere where you see an SR in front, right? Or an S. These are the ones that we had to free in each step. So our model, our final model based on the invariance analysis gives us a different item intercept and gives us two different residual variances, right? So there's basically three measurement model parameter differences between our model, the preferred model, and the structural equation model. One of those involves the mean of an intercept. Two of the other three involve some version of variance, whether it's item level or trait level, right? So that's why they're different. So what I was arguing logically is, right? Yes, the the model that we built was more complex, but the process by building the thing that we did, the measurement and variance analysis, is almost a more flexible version of a structural equation model building process as well too, because you're allowing certain parameters to have like heteroscedastic variances. That's what's happening in this analysis, right? So I point that out because it seems like the measurement and variance part is sort of disjointed in the way I'm teaching the class this year, right? I'm like, oh, structural equation model, it's just path analysis with latent variables. It's just when you start putting them together in the big picture, you have to remember the things that aren't in the path diagram, right? This structural equation model is represented by this diagram. And this diagram we know can't be accurate because we know, for instance, right now, there is a direct effective student on GRI3. So that's a missing path, right? And just like in your regression analyses, if you misspecify a variable, there's a bias that goes on with that. What I don't show here is there's also a difference. Students should also predict the variance. That's what's happening. So what we've done, even though this path diagram seems to put it all together, there's a lot involved in this that are assumed that we're not talking about, and it falls under a bigger picture heading of missing variable or omitted variable bias that we end up seeing. So I wanted to get that point out. I feel like I've just dropped a surprise bomb in class. Like it's just like surprise, like like the gender reveal of SEM. Like, oh look, which by the way, I don't get, but that's just me, and because I'm an old man. Yes.
This is relevant here. So you
No worries.
no one has to check the two models, right?
Yes.
There is something I have used in my analysis, which is last test LRT.
Yes.
So would the outcome be different and why?
This right here. I think it is the same thing. So in R, the summary function, in each package, you can go and adjust how it does it. And you basically have to write your own function. So I think this function here is the same as that. They just embedded it. I may be wrong about that, but I haven't looked at the objects. But
Yeah, like generally
I'm
they
not summary, sorry.
so like because you said that to ignore chi-square test for ANOVA.
Yeah, same result. Yeah,
Yeah.
yeah. I believe they're the same. ANOVA, I said summary before. ANOVA is what we call a generic function in R. So you can attach a package-specific version of it. So I'm guessing lab test LRT is what they just attached to ANOVA when you load the package.
So we don't get like any like understanding if there is like nested or not nested or anything.
Yeah. Well, in this case, if these models are sufficiently different where I can't tell if they're nested. I probably could tell with enough time. I just can't tell on the fly. Let's put it that way. Same with you. I think we could both sit down and try to figure that out. But what I was doing here, I just wanted the tabular way to look at AIC and BIC right by. So I basically knew I was going to ignore this part of the table, and I was going to focus on just this section right here.
So it doesn't matter if the probability is not zero or like 0 point less than 0.05.
These right here, yeah, this probability is irrelevant. Yeah, because I can't guarantee these are nested. In fact, I don't think they are. You can't trust anything over here.
So I just report AIC and BIC and based on that I can do
Yes. Yep. But the other way you can talk about it is, well, no, I think that's sufficient. That is sufficient. Yep. Ironically, the other thing I was going to mention here is let's go back to that last residual model. Nope. Come on, Jonathan. That one. I didn't talk about model fit, but we do have an RMSEA 0.052, and CFI and TLI are better. But now if we compare that model fit, remember, this is the same set of exogenous variables as we have in the SEM model, right? The very first one up here. This model will fit worse. In fact, much worse. right? So had we have looked at our structural equation model, and actually this is the interesting thing. Yes, I created these slides originally, or this example originally 10 years ago, but this is 10 years of experience, right? I left it here last time saying, look, it didn't fit, but why did I show this to you? Well, this model went from a perfectly fitting model to a very bad fitting model by adding one exogenous variable, right? So if you had done this in this framework, there's nothing that would tell you, there's no modification index you could find easily that would put in the parameters that we just found. The measurement and variance technique sort of has to be built into the process as well too. So what I'm trying to tell you with this is, yes, SEM is path diagrams with latent variables, but there's a couple tricks to it. Number one, the measurement models have to be invariant to do SEM. And if they're not invariant, they have to be partially invariant. And if you don't do that, your results are going to be much different than they would be otherwise, right? Yes. So what does that tell you? That tells you just don't even bother. Machine learning will handle all of it. What's that? I don't mean that. I don't mean that. I don't know. It would be lovely to be in a place. This is hard stuff, right? Like the layers, like I can tell you this today and I can teach you this with the benefit of a long time thinking about these problems. It is hard to expect someone to go and get to this level to be able to do things. That's where before we used to have better, collaboration between biostat or statistics or measurement or whatever you want to call it and non-measurement folks to sort of partner with it. But I will say the more that you study this, I don't think this is going away. And I don't know that our AI tools right now are good at doing to this level. Yeah.
Something that kind of struck me is that like if we use this math to build AI models,
Yeah.
like I don't think I find myself getting rid of being like this is the math behind AI in some ways.
Some ways. Each neural network, the architecture is a little different for each a little bit, but definitely a very similar process of a path diagram of some sort, right? Okay. Other questions about this model? Okay, so I wanted to compare what I just did there with a different version of this. So here, this is the model I just had that we said didn't fit. What happens if I predict the items by student too? What is that changing for those?
Are we eliminating the non-student and
So in this case, think of it this way: the measurement model is still the same, and the structural model is the same, but now we're adding a direct effect of the student onto item 5 and item 3. So the parameters, yeah. So let's think of it this way: there would be a direct effect, yes. And let me draw something real quick. Sorry, I got to bring up my QuickTime. My iPad must know it's the last day too. Tell that to Eduroam, or tell that to my password that I mistyped. Let's put it that way. Okay, so if we think about this, GRI 3 was one of those items that had that, right? The measurement model version would have mu3 plus lambda 3 times the factor. Sorry, this is for a person plus error for that person, right? But now what we're adding to it is, take that off. We're adding like a regression coefficient times student for that person plus error for the person. So because student right here is a 0 or a 1 variable, that means what we've effectively done is modified the mean, right? Because when student is 0, you get your original, and when student is 1, the mean, or the intercept, excuse me, the intercept now is the sum of those, right? Right? So what this is is actually what I'm doing here is the building or the beginning of what the very first version of measurement and variance models happen to be. This is called a mimic model. And you still heard this term. This is a term that started in the 1970s. Shortly after structural equation modeling, maximum likelihood went into use, this model came about. And what you can see here, hopefully, is that now we can detect whether or not there's a group difference on the item, the intercepts. So in this case, item 3 has a group difference, item 5 does not. But if you remember from our model that we fit in the invariance process, I think it was item 3 that we had to free for the intercept, and not item 5, not item 1. So this is partially getting closer to what we had before. And you will see now when this happens, our effective gambling has changed, right? It actually got closer to where we were before because we're moving it in the right direction of where we want it to go. Sort of getting better. So I just wanted to point that out. That's called a mimic, multiple indicators, multiple causes model. I think I have slides on that. There we go. This right here. Right there. And the other thing I wanted to point out, so let's do this. Well, I can show it here as well. We do get an R-square report for all the parameters included gambling, right? This is from an example that's sort of based on what we had before. We would still get, so one thing I will note is when you build the structural equation model looking this way, right here, you will note that our gambling intercept isn't listed because it didn't use the Levon function, but it is gambling intercept set to the mean of gambling set to 0, and the variance of gambling is now estimated. So this is a marker item for the variance of gambling, right? But the mean is constant. All right, set to 0. If you wanted to compare that with a non-marker item, right? Here's the comparison. This is old output, but I thought it was relevant, right? So here, when I set gambling to 0, I was trying to show you could, where this R squared came from. Actually, let me hold up 1 second. This is the same. This is with and without the both. No, I want to go with that. Actually, no, this is not the example I thought it was. Never mind. Sorry. This is what I was after, right here. What I wanted to show you is what happens when we fix that variance to 1, the marker item part. This is the other complication I kept dwelling on before. I told you this before, but basically, when we put in the marker item, when we enforce the variance of 1, and it's enforced because in my syntax, I have an std.lv equals true, right? So here, what I've done is I've estimated our slope of student predicting the gambling. Sorry, this is the intercept. And then the intercept student, that was, excuse me. I've estimated the slope of student predicting gambling, but I've fixed the variance to 1 because of the identification of the measurement model, right? See what I'm saying? Whereas in the measurement model itself, actually, let's do this. Let me take off the mimic part because we already know that that's somewhat inefficient. But I wanted to get the point across here. What did I just do? Oh, can't even do it. So this is. I just took this off. This is funny. Cannot estimate it. Okay. Fine. Okay. Well, Never mind then. You get problems. Problems are bad. I broke it. Here, let's do it. I want to compare and contrast for you what happens with both. So here I will fit one with and one without. I have to. Here we go. And again, it didn't work. So this is it. This is where I was like, oh, I can do this live example. Not coming through here. Yeah, tell me about it. Let me go back to try one other thing real quick here. Real data gets me every time. Okay, now it's working for some reason. Huh. Okay, so this is our model if we standardize the factor, right? So we just built a mean of 0, a variance of 1. This is how it works. I get an R square of 0.293. And if I don't standardize the factor, I still get my R square of 0.293, but now you see my variance is now 0.313 and estimated. But take a look at what happens. This is where in structural equation modeling, we sometimes want to allow the variance to be estimated, right? In this model, you can think of us saying, okay, these were my factor loadings. They're probably going to be close to where they were from my measurement model when I use the standardized or the marker item. But if I compare those when I don't, right? Really what I'm trying to say is I am now comparing the wrong thing again. So give me 1 second. If I put a 0 here, what am I doing? I'm actually building a model where I have this as an endogenous variable in my model, but I'm really not changing anything other aspect of my model at all, right? It's just adding a 0. Basically, this is my measurement model with another variable. My model fit gets worse, but my measurement model should be right about the same. I'm doing this to show you that when I don't standardize the latent variable, watch what happens when I estimate versus not estimate that path, right? So here, when I have the gambling variance estimated, our factor loadings into the latent variables, let's just take a look at the STD all column, are somewhere between 0.535 and 0.652, right? Now, when I predict it, those factor loadings, one of them gets a little smaller, but the other two in the same magnitude. Now, that one getting smaller, turns out that's on the item that needed the different intercept, right? That's related. That's going to be related. That's model misfit rearing its ugly head. And this is actually a common phenomenon, right? You fit the measurement model first, but when you combine it with the structural model, the parameters may change. And to the extent the structure or both parts of the model don't fit, the parameters may change quite a bit. Right? That's one thing I wanted to show you. Okay? Now let's compare and contrast that same thing, but when I standardize the latent variable. Right? So first, without the effect. Without the effect, again, not a lot of change, right? With the effect, now these numbers have changed again, right? They're back to where they were, but model is the same. I guess what I'm trying to say here is two things, right? When we do this, we don't like to see these changes. Actually, these changes, the non-standardized ones have changed significantly. That's really what I would dwell on here, right? The non-standardized ones went from, well, no. What am I doing here? That's the variance estimated. And that's, okay, so here we go. This is what I was saying. In the other version, the non-marker item, yeah, they all changed. Anyway, they're wiggling around. When you add the two models together, they wiggle around. That's a problem. The other thing that's a problem is the R squared, while you can, Levon will give you an R squared for gambling. If you had this fixed, you wouldn't be able to calculate it yourself. That's the other part I was trying to talk about. Why is that the case? Because it's always one. In the model where you had estimated the slope versus not, it's no longer residual variance, it's just the same estimate value. Sorry for that confusion. Blah. Turns out I'm going way faster than I expected to. There's one other part I wanted to talk to you about. And that's where what would happen if we estimated this model with the sum score. We just summed up those three items. Hi, my name is Jonathan, and I've done this before. I know, the look on your face. You know what? There's a part of me that's oddly like pleased to see that look, thinking that I wanted to interpret that as I've just sat through this whole semester on not to do this. Okay? Right? I'm glad I recognized that well, because I was like, maybe that tells me I did something good this semester that maybe brought you along with me. Okay. Okay. Sorry. Is that what you call it? I shouldn't be a therapist, but or a counselor, but I just okay. But okay, this is why I'm gonna say this though, because you probably will have this happen to you in your career. If you start doing structural equation models, you're going to have to tell someone why this isn't going to work. So let's think about why this is going. By the way, this is my last example for today. After this class will be over, so I'm not going to have a break. We'll just go a little bit further. Maybe at the 20-minute mark, it may be a little bit further than that. Is that okay?
Yeah.
Okay, cool. So what's wrong? What is different about this, first of all? Right. And from a measurement model perspective, could we actually build a measurement model that equates to this? Potentially. I think we could, actually. It's exactly right. So when you add items up, do you remember the correlation of that sum score with the latent variable from the parallel items model is 1? So now what is the parallel items model? The parallel items model is one where the factor loadings are all set to be equal across items. Unique variances are set to be equal. So we probably, and I haven't done this, I won't do this on the fly. If you want me to, I can do it on the fly. We can see how it works. You want to? Let's just run this model first, right here, and see that our estimate now is 2 points lower. Now, the scale of this is points in the Likert value. Students are 2 points lower on average, so it's a different metric altogether. But to believe this is true, right, we've lost the ability to talk about group differences on items now. We've totally took whatever non-invariance is true in our measurement model and completely lost it, right? And now we're getting an effect that's sort of on the raw score, the actual Likert item points, that, is not there. What I wanted to sort of bring about with this is sort of, you're going to encounter this in your life quite a bit. One of the first, I'm brand new baby doc PhD. I got lucky. I got an academic job I really wanted to get. I'm at the University of Kansas, and I'm on my first committee as the stats guy in the psych department. I'm in the psych department. So I'm sitting there. I met with a student for 6 months every week. I was like gung ho. We're gonna get these analyses done. And it was a structural equation modeling model I was helping with. And they built their proposal. They gave it to their advisor, and you know where this is going, right? The advisor's like, we don't need the structural equation model. We need to do this, right? And so I'm telling you that because that look that you had is still a large part of the rest of the world. And so what we want to be able to do is that's not wrong. That's just a naive point of view, right? And so that's the older me saying this. The younger me was pretty pissed off, right? That was a lot of time. But anyway, student passed. We were all good. I learned a valuable lesson in hindsight. But what I'm saying here is let's make remember how we talked about the measurement arguments you need to make And we talked about that after the midterm. Here's what I would say, right? Number one, you lose this is a bad model because number one, you're assuming parallel items, which is not likely to hold. Number two, even if parallel items did hold, you're now losing the chance of evaluating whether there's group differences on any of the items themselves. So sort of the idea of non-invariance possibly being in place as well too, right? Now I could build an invariance analysis on parallel items and work it up that way, and that might satisfy people. But at that point, if I'm going to do that, why bother, right? Just do the other. So the other part I'm trying to tell you with this is, yes, question.
Sorry, my brain is not real that here.
Me neither.
Why we are doing this?
I'm
Why are
doing.
you doing this model? Because
Okay.
like RAMC and the other things are zero, which is how we
This is just a linear regression right here. Yeah.
okay, so we are not thinking of the item.
No, so what I'm doing here is I'm saying this is what you might have done before you had this class. Yeah, that's sorry, I should have given a better introduction. And no, it's okay. Hey, I'm over here fumbling over what I intended to do with my examples. So here's where I'm going with it, right? Kevin gave me a look that said, why would we do this? And I'm saying, yes, that was the point of this class. But I'm bringing it back up to take what you've learned in this class because there will be times in your life that this is what reviewers or advisors or whomever who don't know structural equation modeling expect to see. And what I want to prepare you for is saying, why? This other approach that we just did took a lot more time, is a lot more complicated. Why can't I just do this and be good with it? Right? And the answer to that would be what? I would say the same thing I mentioned about when we sort of critique the midterm over what do we have to believe for this score to really be used in this way? What do we have to believe for this to be used? No method effects, no group differences on items. That items measure the same construct. They measure it equally well on everybody. Yep.
But in the regression, you can control for variables, right? Like the way we kind of like think of okay, so like if you're thinking of like gender, just like
Yes.
student versus non-student,
Yep.
like we can have that
Yes.
regression model. So like then why like I understand the
This is a great question.
but like then how is
We're controlling for student, you're saying.
yes
Why can't I do that? Well, because what we're saying is that to do that, we're assuming that student doesn't impact each of the items and how they relate to the construct. Right?
we are controlling the whole model based on student and non-student, but like which means that we are not focusing how student versus non-student
Right. Once
each other.
right. Basically, we didn't control for student in this part right here. Right? When we didn't control for student in the summing of items, this is a naive measurement model. I call that, some people don't even call this a model at all. I'll at least call it a naive measurement model. To me, this is equivalent to a parallel items model, right? So we first have to believe the parallel items model exists, it fits well, but then we have to go a step further and say that it's invariant across student, right? Because if we don't, if it's not invariant, then there actually should be a different weight than number one multiplying each of these by group to give us that, to control for it.
So like the way you always talks about the second reviewer.
Oh yeah, reviewer two, yes.
Like to not have a comment like, oh, why did you do this model if when we are doing the whole structural model, should we have this in like should we show this model and say that oh this is not
Let's hope not.
because of that,
Yeah.
which is why I'm doing that.
Yeah, the other problem with that is there's only so much, even though we have everything electronic, page space is a premium, plus reader attention is a premium. So I don't know that it's good to put this down, but in a reply to a reviewer, That's where I would put that information. Where I'd say, and better yet, a better rationale for why you did the structural equation model in the first place. You might put, we're using a structural equation modeling approach to this because it allows us to test for measurement and variance, which the classical approach will not allow us to do easily. Something along those lines, right? And then if a reviewer says, no, 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 you should do it this way, what you could then do it, my reply to the reviewer would be, thank you for the comment, and many people feel the way you do, but here are the assumptions that you have to believe to be true for that to be valid. And basically, we're saying the items measure the same construct, they measure it in the same way, they do it without any bias or any difference across group. And then when that all is the case, then you can believe this. Yes?
Can you contextualize or explain how this will map onto a continuous outcome versus a binary?
Yeah, absolutely. So like if student were continuous,
Yeah.
okay, that gets a little harder because we don't, this multi-group approach doesn't work as well. That does get into the realm of this, what Dan Bauer calls the moderated nonlinear factor analysis. But the idea would be that what we've just done with this multi-group approach and syntax could be done in a regression style approach if we could have an interaction between the group variable student and the latent variable gambling. Like basically, it becomes an analysis of covariance. So when it's continuous variable, that not this multiple group approach happens. You could go into the moderated nonlinear factor analysis approach to it. That is harder in some ways because there's less software available, other than there's an R package, and so it's fairly advanced. And where I would go with it, I know this doesn't help you in this class, but if you have a continuous variable, I would either people will tend to break that into different groups. It's probably not a great idea. Or a Bayesian framework that does the moderated nonlinear factor analysis may be a little better. Yeah, I know. That's right. Yes. So if it's, yeah, let me see if I can get back to where we were here. So we're predicting the mean. Yeah, I think this should work for that then. Yeah. Mm-hmm. Yeah. How's that work for everybody? See what I'm saying? Like, yeah, when you have a non-categorical group variable. The other thing where this gets hard is if you have 3 different group variables, right? Then it's every permutation becomes a group. And now you have 8 group analysis. There's only so many groups the multi-group approach will work for. Beyond that is a pretty advanced topic at the moment. It's getting better, getting easier. But if you're in that situation, you know where to find me. I'm still on the internet. I may not be at Iowa, but I would welcome an email or a conversation from you. And if you'd like to fly out. So I still haven't said to YouTube where I'm going, so the YouTube is not going to know. But YouTube, you can put it in the comments. Where is Jonathan going to work? Or is he? Got to make it there, January 1st. Yes. So that was today. It was sort of a mixed match of where we were at, what we're going. It's funny because in teaching this class, it's a really well-developed methodology. Like this is something that, and it's driven largely in social science. Some of the bigger names of this, either psychology, sociology, statistics and social science. And so when you're in social and educational sciences, you're like, this is the universe to us. And then you don't realize how big that is compared to the rest of the world, right? And now the rest of the world has all the machine learning and all the other tools with it. And so one of the interesting things I wanted to mention about this methodology is it incorporates multi-level aspects as well that you don't see in a lot of data science or machine learning type methods, right? What I mean by that is now we're controlling for items nested within person and how that depends. And we have, different effects at different levels potentially. And this may even also be multi-level. But with all that being said, it's a mature field that even people in the social sciences aren't super familiar with. So you got to expect that the people you're going to work with, you're going to be teaching them. But that's okay. My advice to you is don't be like me, right? Try to be like, yeah, I thought that too. Validate their feelings. I'm trying to. This is where I could use your help, Tevin. Where I feel like I'm doing statistical counseling. Right? So there is a statistical. I took a stat consulting class in grad school. It was awesome. I was able to work with people and see how the professional statisticians would ask them about their data problems and work through it. And I learned so much about how to talk to people about data from that. I wish we had more experiences like that. So yeah, no, I think that's like a practicum with it. But I hope that you have been able to get things out of this class. I will tell you that I appreciate your patience with me during the Spirit Airlines semester. The spot surveys are available on Icon. Please do. I encourage you to fill those out. I will look at your responses. They usually come the day after Christmas, which is really like I tend to not want to open them then. Like I just, I'm not a big celebratory guy, but at the same time, I'm kind of like, that's one of the days of the year I don't want to think about like criticism of anything. But please do, I encourage you to fill that up. And then finally, I will be updating Icon to have the details about the final that you all know about, but just you're welcome to sit in the room and even use the Zoom on the computer if you have nowhere else to go. I just won't be present next week, but I'm intending for us to be on Zoom. Okay?
Yeah, the presentation is the final.
Presentation is our the final presentation. Yes. Okay. Anything else then? Well, thank you all for a great semester. Clap for you too. You made it. And I want to thank the University of Iowa for the opportunity to have worked here. So there we go.